Right. So welcome back to today's EMS session. Very good morning to you all. Let me recollect the topic which I have discussed in my last class. So in my last class, I have discussed about the polarization. So what is polarization? Polarization is the behavior of electric field component at some fixed point in space, or the orientation of electric field strength in space with respect to time is called as polarization. Right? How electric field is changing in space, right, is called as polarization. And depending on how electric field strength changes in space, polarization can be divided into different types. Number one, linear polarization; two, circular polarization; and three, elliptical polarization. Right. So the name itself will gives you how the electric field is changing. Linear means the electric field is changing linearly, and circular means the electric field orientation is circle, and elliptical means the electric field is changing elliptical. Right. So linear polarization. So linear polarization, as I have explained in my last class, at every point of time, the electric field component is linear. All right. In other words, is constant. Right. And depending on the electric field component, whether it is parallel or vertical, or whether it is vertical or horizontal, we have two subtypes: linear vertical polarization and a linear horizontal polarization. When electric field is vertical, it is linear vertical polarization. When electric field is horizontal to the plane of polarization, then it is a linear horizontal polarization. And coming to circular polarization, so in circular polarization, the electric field components are equal in amplitude. Right. Electric field component are equal in amplitude. That means Ex is equal to Ey. Right. Electric field in x direction and electric field in y direction, magnitudes are equal, and they are out of phase by 90 degrees. It is called as circular polarization. And elliptically polarized wave, in the sense the amplitudes are different. So that is only the difference between circular polarization and elliptical polarization. In circular polarization, amplitudes are equal, and whereas in elliptical polarization, the amplitudes are unequal, but they are out of phase by 90 degrees. Right. Let us move on to another new topic, and a very important topic today. A reflection of plane wave, normal incidence. A reflection of plane wave, normal instance. So that is what we are going to discuss in our today's class. And as we know that, let me explain what is meant by reflection. So in general, right, in general, and let us say this is the boundary, and let us say this is region 1 and this is region 2. Right. When EM wave travels and incidence on the boundary, when EM wave travels and incidence on the boundary, in general, part of wave transmits part of wave transmits and part of the wave reflects back, right? Part of the wave transmits and part of the wave reflects back, and this is called as incident wave, and this is called as a reflected wave, and this is called as transmitted wave, right? So therefore, when wave incidents on the boundary, part of the wave reflects back, right? Part of the wave reflects back, and reflection of the wave depends on the boundary, right? Reflection of wave depends on the boundary, type of boundary, right? So type of boundary in the sense, for example, region 1 is free space and region 2 is dielectric material. In other words, region 1 is free space and region 2 is a conductor, and region 1 is free a dielectric material, right? Region 1 is dielectric material and region 2 is a dielectric material, like that, right? So when region 1 is free space, when region 1 is free space and region 2 is a dielectric material, the boundary is called as free space dielectric boundary, right? Free space dielectric boundary, right? So and depending on how wave incidents on the boundary, on the boundary, we have different categories, right? So for example, here, so this is the boundary. If the wave incidents normally like this, right? The wave incidents normally, it is called as normal incidence, right? So this is the boundary. When the wave incidents normally with exactly 90 degrees on the boundary, it is called as normal incidence. When the wave incidents with a certain angle on the boundary, when the wave incidents with a certain angle on the boundary, so this is called as theta I, right? So theta I is called as angle of incidence, right? Angle of incidence. When angle of incidence theta I is equal to 0, it is normal incidence, right? When theta I is equal to 0, it is normal incidence. When theta I is not equal to 0, it is called as oblique incidence, right? Oblique incidence or inclined, right? Inclined instance, right? So these are the two types of instances: normal instance and oblique instance, right? Normal instance. So this is normal instance and this is oblique instance, right? And we are going to discuss about how EM wave behaves when EM wave instance normally, and how EM wave behaves when EM wave instance oblique in nature, right? So those things we are going to discuss, right? So those are the two very important topics which we are going to discuss now, right? So for this class, as I have given the heading reflection of plane wave normal instance, so I will discuss the normal instance in this class, right? Normal incidence. So normal instance, what is meant by normal instance? Let us say here I will consider a boundary. It may be any type of boundary, right? So this is a boundary. Here I'm considering a boundary, right? So this is boundary between two regions. So this is region 1 and this is region 2. Region 1 is characterized by sigma 1, epsilon 1, mu 1, and region 2 is characterized by sigma 2, epsilon 2, mu 2, right? So because earlier we have defined different media based on their characteristics, right? For example, free space. What are the characteristics of free space? Sigma is equal to 0, epsilon is equal to epsilon naught, mu is equal to mu naught. And similarly, lossless dielectric, sigma is equal to 0, epsilon is equal to epsilon naught epsilon r, mu is equal to mu r mu naught, and like that we have defined the characteristics of different medias, right? So therefore, medium 1 is characterized by sigma 1, epsilon 1, mu 1, and medium 2 is characterized by sigma 2, epsilon 2, and mu 2, right? So this is the normal instance, right? So this is the normal instance. Let us say, and this is x, and let us assume that the wave is propagating in z direction, right? The wave is propagating in z direction, right? So that means like this. In this way, the wave is propagating, right? So in region 1, the wave is propagating in region 1, meets the boundary, and enters into another media, right? Enters into another media, right? Like this, right? So now, as we know that when wave is propagating, right? When wave is EM wave is propagating. EM wave in the sense what? Which contains electric field and magnetic field components, right? So let us say those can be represented like this. So this is the direction of wave propagation, and let us say this is the direction of incident electric field, and direction of magnetic field is this one, right? So EI, instant electric field, is moving in x direction. Instant magnetic field is moving. What is the direction of magnetic field here? Dot and a circle means dot is encircled, means what? The magnetic field is coming outside, right? Coming outside on the screen, your screen, let us say, right? So coming outside the screen in the sense what? This is y-axis, right? So this is y-axis. Therefore, it is in y direction. Magnetic field is in y direction, right? So this is about instant EM wave, right? When this instant EM wave meets the boundary, what happens? Part of the wave transmits and part of the wave reflects back, right? So therefore, part of the wave transmits like this. So direction of wave propagation does not changes. Direction of wave propagation remains same, and direction of electric field also remains unchanged, remains same, and direction of magnet. This is ET, right? ET, and this is HT. So ET in the sense transmitted electric field, and HT in the sense transmitted magnetic field, right? So this is how we can represent transmitted wave, and part of the wave reflects back, right? Part of the wave reflects back. So when part of the wave reflects back, this is the direction of wave propagation, right? So wave propagates in negative z direction, and direction of electric field remains unchanged, ER, reflected electric field, but the direction of magnetic field will be like this. That means inside, right? Direction of wave. So here dot with a circle is magnetic field is out, and with cross means magnetic field is in, right? So the direction of magnetic field in the starting of magnetic field is magnetostatic field itself, I have discussed, right? So dot with a circle, H is out, and dot with a cross, cross with a circle is H is in, right? So therefore, and one more, if you want a more clarification, I will and discuss in incident wave. So in if incident wave, if you consider incident wave, right? So what is the direction of electric? As we know that the relationship between direction of electric field, direction of magnetic field, and direction of wave propagation is this. So this is the relationship between direction of electric field, direction of magnetic field, and direction of wave propagation, right? So this is the relationship because all are mutually perpendicular. The direction of electric field, magnetic field, and direction of wave propagation are mutually perpendicular, right? So if you consider an incident wave, what is the direction of electric field? Ax bar. And what is the direction of magnetic field? Ay bar. And the direction of wave propagation is Az bar, right? So it is satisfied. So this equation is satisfied. Ax bar cross Ay bar is Az bar, that we know. And similarly, reflected wave. If you consider a reflected wave, right? If you consider a reflected wave, what is the direction of electric field? For a reflected wave, the direction of electric field is unchanged, Ax bar, right? And direction of magnetic field, let us say Ah bar is equal to, what is the direction of wave propagation? Minus Az bar, right? This one, this I have written right here, right? Reflected wave, right? So direction of electric field is Ax bar, direction of magnetic field, let us say we don't know, and the direction of wave propagation, what is the direction of wave propagation? Reflected wave, negative z direction, right? Negative z. Then what is Ah bar? What is Ah bar? Ah bar is equal to minus Ay bar, right? Ah bar is equal to minus Ay bar, right? So therefore Ax bar, right? Ax bar cross minus Ay bar is equal to minus Az bar. So therefore this equation is satisfied, right? So therefore wave to change its direction, right? Wave to change its direction, the direction of magnetic field should be changed, right? So whenever the direction of magnetic field changes, then the wave direction changes in opposite direction, right? So this is about indicating incident wave, transmitted wave, and reflected wave like this as shown in figure, right? So the figure is very important, right? So incident wave, transmitted wave, and reflected wave, right? So here from the figure, Ei and Hi are incident electric and magnetic fields respectively. Similarly, Et and Ht are transmitted electric and magnetic fields respectively. Er and Hr are reflected electric and magnetic fields respectively, right? So now incident fields, right? Incident fields can be written like this. Ei is equal to Ei naught e power minus gamma 1 z, and this is equation 1, right? Electric field or magnetic field can be expressed in phasor form like this, right? So where gamma 1 means propagation constant, right? Propagation constant in region 1, right? In region 1. And if you see if you look at this figure, instant wave and reflected waves are in region 1, and in region 2 we have transmitted wave only, right? In region 1 we have instant wave and reflected wave, and in region 2 we have transmitted wave, right? So therefore instant wave, instant electric field, ei is equal to ei naught. Ei naught is the magnitude of instant electric field, e power minus gamma 1 z, minus z in the sense what, the wave is propagating in positive z direction, right? So e power minus gamma z means the wave is propagating in positive z direction, right? Positive z direction. E power plus gamma z in the sense what, e power plus z, e power plus z in the sense the wave is propagating in negative z direction, right? So that you remember. And similarly magnetic field component hi bar is equal to hi naught e power minus gamma 1 z, right? Minus gamma 1 z. And one more thing, ax bar, right? Electric field is propagating in x direction, and magnetic field is propagating in y direction, right? So here we have seen, so magnetic field, electric field is propagating in x direction, magnetic field is propagating in y direction, right? So therefore here ax bar, electric field is propagating in x direction, and magnetic field is propagating in y direction, right? So this can be written as, this is equal to ei naught divided by eta 1 e power minus gamma 1 z ay bar, and let us say this is equation 1. Since e by h is equal to eta, right? So this relation we know, the relationship between electric field and magnetic field, e by h. So what is e by h? E by h is equal to eta, right? So therefore from this what is h? H is equal to e by eta, right? H is equal to e by eta 1. Why eta 1? Because instant field is in region 1, right? It is in region 1. So therefore electric field and magnetic field of instant wave can be represented like this, right? Represented from equation 1 and equation 2, right? And similarly reflected waves, let us see reflected fields or waves, right? Reflected wave. So er bar is equal to er naught e power gamma 1 z ax bar, right? So this is equation 3, right? So this is the reflected electric field. Er is equal to er naught is the amplitude, and e power plus gamma 1 z, right? Have you find the difference here? E power plus gamma 1 z. So e power plus gamma 1 z in the sense the wave is propagating in negative z direction. Reflected means the wave changed its direction, right? The wave changed its direction to opposite, right? So therefore er naught e power plus gamma 1 z AX bar, gamma 1 because reflected wave belongs to region 1, right? And similarly, magnetic field. So what is magnetic field component? HR bar is equal to HR naught e power gamma 1 Z minus AY bar, right? Minus AY bar, right? So because here we have seen when wave changes its direction, the magnetic field direction also changes. Here you can see, right? So when direction of magnetic field change, so this is the direction of magnetic field minus AY bar. So when magnetic field direction changes, the direction of wave propagation will also changes, vice versa. These statements we can say vice versa, right? So therefore the direction of magnetic field is minus AY bar, right? Minus AY, and this can be written as minus E R naught by eta 1 e power gamma 1 Z AY bar, and let us say this is equation 4, since E by H is equal to eta, right? So H is equal to E by eta, right? So this is equal. So this is how we can represent reflected waves, reflected electric field and reflected magnetic field, right? And now transmitted waves, waves or fields, right? Transmitted waves. So what are the transmitted wave? Transmitted electric field, right? Transmitted electric field is equal to E T naught e power minus gamma 2 Z AX bar, and this is equation 5, right? Transmitted wave. So what is the direction of transmitted wave? Still in positive Z direction, right? It is still in positive Z direction, and the transmitted wave is in region 2. So therefore gamma 2 from figure. So from the figure only I'm writing, right? From the figure I'm writing, right? So here you can see from the figure, here this is region 2, right? And this is region 1. In region 2 we have transmitted wave. In region 2 we have transmitted wave, and whereas in region 1 we have incident and reflected wave, right? So incident wave direction is AZ bar, and reflected wave direction is minus AZ bar, and the transmitted wave direction is AZ bar, right? And in all these three cases, that is incident, reflected and transmitted wave, the direction of electric field remains same, right? EI AX bar, ET AX bar, ER AX bar. So that direction of electric field is not changing, it remains same. But whereas the direction of magnetic field is changing. For reflected wave, the direction of magnetic field is negative Y direction, right? This is how, right? And coming to the transmitted magnetic field, right? Transmitted magnetic field can be written like this: HT bar is equal to HT naught e power minus gamma 2 Z AY bar, right? Plus AY bar, right? Because here dot, right? So in instant wave and in transmitted wave, the magnetic field is represented with dot with a circle, right? Dot with a circle. So dot with a circle in the sense the direction of wave propagation is in positive Y direction, and cross with a circle means the direction of magnetic field is in a negative Y direction, right? So therefore and this can be written like this. So this is equal to et naught divided by eta 2 and e power minus gamma 2 Z A Y bar, and this is equation 6, right? So therefore And this is how we can write, right? We can write the incident, reflected and transmitted waves, right? So instant waves, equation 1 and 2, reflected waves, equations 3 and 4, and transmitted waves, equation 5 and 6 are the transmitted waves, right? And magnetic field in region 1 and in region 2. So what is the total uh, um, electric field and magnetic field, right? So we can notice, we can notice the figure that the total field, in medium 1, the total field in medium 1 comprises of what? Instant and reflected waves, right? Instant and reflected waves, whereas medium 2 comprises of only transmitted wave, right? Comprises of only with the transmitted waves, right? Here in the figure we can see, right? So region 1 contains instant and reflected waves, and region 2 contains only transmitted waves, right? So therefore we can write that the total electric field in medium 1, right? The total electric field in medium 1 is equal to EI plus ER, right? The total electric field in medium 1. So what is the total electric field in medium 1? Instant plus reflected wave. And similarly, magnetic field. The total magnetic field in medium 1 is HI plus HR, right? So similarly, the total electric field in medium 2. So what is the total electric field in medium 2? ET, only ET. And the total magnetic field in medium 2 is HT, right? We have only transmitted fields in medium 2, right? So this is medium 1, right? So this is medium 1 and this is medium 2. So in medium 1, the total electric field is the sum of instant and reflected waves, and in medium 2, the total electric field is transmitted electric field, right? So now here, applying boundary conditions, applying boundary, conditions. In fact, I have not discussed the boundary conditions, right? So later I will discuss the boundary conditions. If time permits me, I will discuss the boundary conditions, right? So boundary conditions says that the tangential component of electric field and magnetic field are continuous, right? Boundary conditions, boundary conditions states that the tangential component is continuous, right? Tangential components. What is meant by tangential component? Let us say, so this is the boundary, right? So this is the boundary, right? So electric field and magnetic field, both electric and magnetic field can be decomposed into two components. right? They can be decomposed into two components. One is tangential component and another one is normal component. So for example, if you consider the electric field here, so what is the tangential component? Tangential component means the component which is parallel with the boundary. So this is the tangential component of electric. Normal component in the sense the field which is normal to the boundary, right? So this is normal component, right? So tangential electric field and normal electric field, right? And the resultant electric field is this one, right? The resultant electric field ER is the resultant electric field, right? So tangential component may be in x direction, normal component may be in y direction, whatever it may be, right? I'm not considering a coordinates here, right? So tangential component, if as an example, if tangential component is x direction, normal component is y direction, like that, right? So and similarly for magnetic field also we can consider tangential components. What is the tangential component? This is the tangential component, right? So tangential component of magnetic field and normal component, normal component of magnetic field, right? So tangential in the sense parallel to the boundary. Now, if the boundary is curvature like this, so this is the curve, then here this is the tangential component. Here this is the tangential component, and here this is the tangential component, right? So like the tangential component depends on the boundary, right? At what point on boundary we are considering, depending on that the tangential component. If this is the tangential component, automatically this is the normal, and automatically this is the normal component, and automatically this is the normal component. So this is how we can undefine tangential component and normal component, right? So therefore boundary conditions says that the tangential component is continuous, right? So continuous in the sense what, let us say this is the boundary as we have assumed above. So this is the boundary. So tangential boundary at z is equal to 0, right? Boundary at z is equal to 0, right? So in this figure also we have considered. So this is positive z direction, right? And the boundary, so what is the boundary? Boundary is at z is equal to 0, right? Boundary is at we have considered the boundary at z is equal to 0, right? Therefore at z is equal to 0, the tangential component is continuous in the sense what at the boundary the electric field, tangential component of electric field in region 1 and tangential component of electric field in region 2 continuous in the sense there will not be any change, right? There will not be any change in the properties of electric field at the boundary. They remain same, right? So in tangential normal component may vary, right? Normal component they may not be same, right? So they differ. But whereas the tangential component of electric field is continuous, that means when wave travels from one media to the another media, there will not be any changes in the characteristics of electric field, right? So that is called as continuous, right? So therefore from this discussion we can write that, right? From this discussion we can write that E1 is equal to E2, and similarly H1 is equal to H2, and this is only at z is equal to 0. When z is not equal to 0, this will not apply, right? So therefore at z is equal to 0, total electric field, the tangential component of electric field in region 1 is equal to the tangential component of electric field in region 2, and similarly tangential component of magnetic field in region 1 is equal to tangential component of magnetic field in region 2, right? So that is the boundary condition. So therefore from this we can write EI plus ER is equal to ET, and similarly hi plus hr. Okay, let me write hi plus hr is equal to ht, right? And let us say this is equation 7 and this is equation 8, right? Next, ei er et. So what is ei er et? So what is ei? Ei is equation 1, er is equation 3, and et is equation 5, right? Therefore from equations 1, 3 and 5, right? 1, 3 and 5 we can write, right? From equations 1, 3 and 5, and equation 7 becomes, right? Equation 7 becomes ei is equal to ei naught e power minus gamma 1 z ax bar reflected field plus er naught e power gamma 1 z ax bar is equal to transmitted field. So what is transmitted field? Et naught e power minus gamma 2z ax bar, right? Substituting equations 1, 3 and 5, substituting in equation 7, right? We will get this one, right? So similarly hi hr ht. So what is hi hr ht here? So you can see, right? Hi is equation 2 hi, and hr is equation 4, and ht is equation 6, right? So even number of equations, right? So from even number of equations, that is from, right, from equations 2, 4 and 6, and equation 8 becomes, let us say this is equation 9, right? So equation 8 becomes hi. So what is hi? Hi is ei naught by eta 1 e power minus gamma 1 z ay bar reflected field. So what is reflected field? Reflected field is er naught by eta 1 e power gamma 1 z minus ay bar is equal to transmitted field. So transmitted field et naught by eta 2 e power minus gamma 1 z ay bar, right? And let us say this is equation number 10, right? And now uh, equation 9 and equation 10 is valid only at the boundary, right? So that means what? At z is equal to 0, right? At z is equal to 0, equation 9 and equation 10 becomes, right, at the boundary. Equation 9 and equation 10, they are valid at the boundary. So therefore at the boundary, in the sense what? At z is equal to 0, right? So therefore at z is equal to 0, equation 9 and equation 10 becomes what? E power 0. E power 0 is 1, right? So therefore from equation 9, e I naught plus e r naught is equal to e t naught. Let us say this is equation 11, and similarly equation 10 will become, so equation 10 will becomes how? E I naught divided by eta 1 minus e r naught divided by eta 1 is equal to e t naught divided by eta 2, and let us say this is equation 12, right? So now we have equations 11 and equation 12, right? So solving equation 11 and 12, and we can determine the, and one more thing, I have forgotten to define some parameters here, right? So as I have discussed here, when EM wave instance, right? So from this figure, you can listen like this, right? So here, when EM wave instance on the boundary, in general, what happens? Part of the wave transmits and part of the wave reflects back, right? How much wave is transmitted and how much wave is reflected? How much wave is transmitted and how much wave is reflected, and that we can calculate from the transmission coefficient and reflection coefficient, right? So transmission coefficient will gives you how much wave is transmitted, and reflection coefficient will gives you the coefficient by which the wave is reflected, that we can calculate, right? So let me define transmission coefficient and reflection coefficient first, right? So reflection coefficient, right? So reflection coefficient is denoted by capital gamma. So this is the symbol, and it is the ratio. It is the ratio between uh, reflected wave to the incident wave, right? It is the ratio between reflected wave to the instant wave, right? So therefore, reflection coefficient is equal to E R naught divided by E I naught, right? So this is reflection coefficient, and let us say this is equation 13, and similarly transmission coefficient. Transmission coefficient. Transmission coefficient is denoted by tau. It is the ratio between transmitted wave to the incident wave. In other words, transmitted electric field to the incident electric field, right? So therefore, tau is equal to E T naught divided by E I naught, right? So this is defined as a transmission coefficient, and this is equation 14, right? So reflection coefficient and transmission coefficient. Reflection coefficient is the ratio between ER naught and EI naught, and transmission coefficient is the ratio between ET naught and EI naught. So therefore, solving equations 11 and 12, right? Solving equations 11 and 12. So 11 and 12, and find out the ratio ER naught by EI naught, you will get reflection coefficient, and find out the ratio between ET naught and EI naught, you will get transmission coefficient, right? So therefore, solving equations 11 and 12, right? Solving equations 11 and 12, you will get the reflection coefficient and transmission coefficient, right? How do you solve? Very simple. If you substitute ET naught here, right? If you substitute ET naught, so what is ET naught? EI naught plus ER naught, right? So if you substitute ET naught here, this entire equation will become a function of EI naught and ER naught, right? So we can eliminate ET naught, right? So if you substitute ET naught here, this will become a function of EI naught and ER naught. Therefore, find out the ratio. ER naught by EI naught, right? ER naught by EI naught, and you'll get the ratio ER naught by EI naught. And similarly, find out ER naught in the second step, right? Find out ER naught and substitute ER naught here, right? Find out ER naught. What is ER naught here? ET naught minus EI naught. So if you substitute ET naught minus EI naught here, then this equation will become EI naught and ET naught. And find out the ratio ET naught by EI naught, you'll get the transmission coefficient, right? So therefore, if you do so, the reflection coefficient will be like this: eta 2 minus eta 1 by eta 2 plus eta 1. You solve it later. And similarly, the transmission coefficient tau is 2 eta 2 by eta 1 plus eta 2. So this is the transmission coefficient, right? So where eta 1 is intrinsic impedance, right? Eta 1 is intrinsic impedance in medium 1, and eta 2 is intrinsic impedance in medium 2, right? So you can find this one, right? Solving equations 11 and 12, right? Solving equations 11 and 12 for the ratio ER naught by EI naught, ET naught by EI naught, you will get these equations. That's very important, right? So this is how we can find out the transmission coefficient and reflection coefficient, and this is about the reflection of plane wave normal instance, right? Reflection of plane wave normal instance. Very simple, right? So the procedure is very simple. If you go through twice or thrice, then it will become very easy, right? So very easy to answer the question from this topic, right? So it is already time. So thank you very much for your patient listening. Just a minute.